This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, good afternoon everyone. When you're ready, we'll make a start. So the plan today is to continue looking at part 4 of the notes, and really what we're doing here is continuing to look at more examples to help us see how to go about designing a feedback controller. And we've already seen lots of examples, for example in problem set 4, which was really about controller design. So we're going to continue in that way. So I want you to think of the things that we're going to look at as examples. They're certainly not recipes to follow. And in fact, you will see that the outcome of the designs that we try won't always work out. Okay, so there is no such thing as a recipe that you can blindly follow without thinking about what you're doing and end up with a controller that meets your specifications. All right? And part of the reason for that is that sometimes we use approximations to guide our design choices, and it's important to account for the fact that they are approximations. And one such approximation that's often used in design is to think of the closed-loop sensitivity function, right? So this guy here, the ratio of the open-loop transfer function and 1 plus the open-loop transfer function. That is the transfer function that relates the reference input to the output, okay, in terms of canonical second-order dynamics. And the reason for doing that is, well, if we have a classical loop shape that has high gain at low frequency, which, as we've seen many times, is needed to get low sensitivity to output disturbances or low sensitivity of the error signal to the reference signal, which will mean that the output is tracking the reference signal. We need high gain of the open loop transfer function at low frequency. And to get low sensitivity to measurement noise and modelling uncertainty, we need low gain at high frequency. It's going to make a transition and cross over somewhere in between. And for a classical loop shape like that, the complementary sensitivity function, the mapping from the reference to the output, will look like this. It'll be close to 1 at low frequencies. It'll roll off at high frequencies. And what it does in the middle really depends on the phase margin, okay? And so it might go down like this, okay? But that would correspond to canonical second-order dynamics with a damping factor bigger than 1, right? Whereas if the phase margin is small, so if the phase of the open loop transfer function is close to minus pi, then you can get some peaking in the sensitivity function, and that would be consistent with having a damping factor that is less than 1. And the smaller the damping factor, the bigger the peaking you would get, and that would be the result of having the phase of the open loop transfer function very close to minus pi radians. Okay, so for a classical open loop shape, right, which we've justified many times, okay, gives rise to a complementary sensitivity function that looks like canonical second-order dynamics, okay, but it's not going to be exactly right because a closed-loop system won't just have 2 poles necessarily. Okay, it depends on the situation. But thinking of the complementary sensitivity function in this way allows us to translate time domain specifications into frequency domain specifications. All right? We know that as long as the damping remains close to 1, increasing the natural frequency, which will correspond to moving this to the right this way without this peaking up much, will lead to a smaller settling time. Okay, but if increasing the natural frequency, pushing this to the right results in more peaking here, a reduction of the damping, then it will only increase the rise time and won't necessarily, reduce the rise time, won't necessarily reduce the settling time. Okay, and we know that the damping is going to be related to, how oscillatory the response is. The lower the damping, the more oscillations there are as the transient part of the response decays to 0, which will happen if the closed loop is stable. Right. So we left off last time, looking at this stuff here, which is really about trying to relate time domain specifications, such as how much overshoot we're prepared to have in the step response of the closed loop, and settling time into damping and natural frequency constraints for canonical second-order dynamics, okay, which we can then translate into phase margin specifications and crossover specifications on the basis of this being a loop shape that looks like this that yields canonical second-order dynamics, as shown here. All right. So this is an approximation that we often make to try to facilitate translation of these time domain specifications into frequency domain specifications so that we can focus on controller design to meet these specifications, right? Because it's easy to think of control system design in terms of compensating the open loop plant with the controller to get the desired loop shape, right, with the right crossover frequency and the right phase margin. So these plots here are really just showing what these expressions look like, right, and this expression here, right. So the amount of overshoot you get for canonical second-order dynamics is related to the damping. The smaller the damping, the bigger the overshoot, right. The settling time is related to the time constant of the poles here, right? So you'll get, when the damping is less than 1, you'll get a pair of complex conjugate poles, okay? The real part of those poles will be the product of the damping factor and the natural frequency, right? So the time constant associated with that is 1 over the real part of the poles, right? And we know that the transient response will almost have decayed away completely after about 4 time constants. Okay. All right. So these plots are just showing what those equations look like, and you can use them, for example, to say, well, if I want 20%, I want the overshoot to be less than 20%, right? I need the damping ratio to be more than 0.45, say. And the damping ratio will correspond to a phase margin of about 45 degrees, assuming I can make my open loop shape look like this, right? At least around the crossover frequency, all right? And then you can use this plot here to figure out what the crossover frequency should be, right? So we've figured out what the damping should be, you get a corresponding normalised frequency, which is just the ratio of the crossover frequency and the natural frequency. All right, so this is just about translating time domain specifications into frequency domain specifications, and it's a good approximation as long as your actual loop shapes, right, which you might end up with one like this, which is this one here, and one like this, which is this one here, having sufficiently high gain at low frequency, low gain at high frequency, and looking like this ideal loop shape, which is shown as dotted lines at around crossover. The ideal loop shape being this one here, which would give you exactly canonical second-order dynamics. All right? So what we're going to do for the rest of today is look at different types of compensator structures that can help you meet specifications once you've identified the specifications that need to be met. All right? So the point is that we're given a plant transfer function, all right? And we're trying to design a controller transfer function to give us a desired open loop transfer function that will have a specified crossover frequency, a specified phase margin, enough gain at low frequency to meet steady state specifications. All right? And this is often achieved by considering very simply parameterized controller structures, right? Ranging from just considering a constant gain, which is going to change the magnitude plot in the same way at all frequencies without changing the phase of the open loop plant transfer function, to lead compensators that can be used to adjust the phase of the open loop transfer function. So at the desired crossover frequency, you meet phase margin specifications, which, as we've seen before, will relate to how much peaking you get in the closed loop sensitivity functions, which will relate to how oscillatory the step response of the closed loop will be, right? Things like lag compensators, which allow you to pump up the gain at low frequencies without interfering too much with what's happening at high frequencies, because maybe, you know, the plant already has the right phase characteristics around crossover, and you don't want to play around with that too much, but you want to increase the gain at low frequencies to give you better steady state error performance, right? Remember, what's happening at crossover frequency is not about steady state, right? It's about the transients. Okay, so if the transients are kind of okay by just closing the loop, but you don't have enough gain at low frequency, then you use something like a lag compensator. A PID compensator is really just putting a lead and a lag compensator together, all right? And it's important to note that sometimes, depending on the plant transfer function that you have, you might have to put many of these things together in order to meet your specifications, all right? So we've already spent a lot of time looking at proportional gain controllers. Okay, so these are just constant gain controllers. You know, as we've seen before, they will change the shape of the plant transfer function across frequency in the same way at all frequencies. It'll shift it up and down without changing how the phase varies across frequencies. And you know, a reason for often for increasing the gain of the open loop transfer function is to meet steady state performance specifications. Okay, so we've seen many times that, you know, the steady state error for a given reference signal is given by this expression here, assuming that the error reaches a constant value, which it will if the closed loop is stable and the reference is a step. Okay, and so we know that the steady state error is given by this when we have a step reference, and clearly increasing K, making K bigger, makes the steady state error smaller. All right, but it's all about what's happening at low frequency. In particular, it's about what's happening at zero frequency. Okay, so steady state specifications are all about what's happening at very low frequency, at zero frequency, in fact. All right. Now, you know, in general, the steady state error for a unit ramp a unit ramp reference will be infinite unless you know, your plant transfer function has an integrator in it, right? If we're just using a constant gain controller, all right, because that would be required to cancel out both the S's in the Laplace transform for a ramp. Okay, so you know, if your plant transfer function looks like this, then your 1 on 1 plus kg S will have an extra S on the top, right? Okay, because that little S there will come up onto the top, and that will help cancel one of those, and then this one cancels out the other one. Whoops, what happened there? Oops. Reset. Okay, so we've seen this sort of stuff many times, right? Increasing the gain of a constant gain controller will typically push the crossover frequency to the right, right? If the gain of the controller is bigger than 1. Okay, we've seen that many times. So that, you know, will broaden, you know, the range of frequencies over which the error signal is insensitive to variation of the reference and disturbances. But it'll narrow the band of frequencies over which the closed loop is insensitive to sensor noise and model uncertainties. That's an example of a design trade-off. Okay. It's important to realise, I don't know what those tildes are there, that's a typo, they shouldn't be there. It's important to realise that, you know, constant gain, high gain control can lead to instability even in what you might suspect are benign situations. A stable plant with no right half plane zeros, okay? It could be the case that, so that's all this is really saying, right? You know, if these things mean that the plant transfer function has no poles or zeros in the right half plane, okay? And I guess the point of this is to say, well, even in benign situations like this, what you might think is benign, closing the loop with too much gain in your constant gain controller can lead to instability, even in these seemingly benign situations, right? So we've in fact seen that before. If the relative degree is bigger than or equal to 3, right, as we increase the gain, parts of the root locus will approach zeros at infinity along asymptotes, and if our relative degree is 3 or more, some of those asymptotes will end up in the right half plane. And so that's telling you if you make the gain too big, you'll end up with closed loop poles in the right half plane. All right, so this is just really a warning, right? Just because things are simple doesn't mean it will work out. All right? Of course, if the plant does have right half plane zeros, from root locus analysis, we know if we push the gain up too high, right, because the root locus approaches the zeros, right, you will end up with a closed loop pole close to the open loop zero in the right half plane for sufficiently large gain. All right? So even in simple situations, you've got to take care. All right? You can't just arbitrarily pump up the gain in order to reduce the steady state error. I think that's the message of this page. All right? So we've seen these sorts of things many times before, right? Using root locus type analysis to understand how the closed loop poles move around as we vary a constant gain controller. We know that the closed loop poles start off close to the open loop poles. All right? And in this case, which is a relative degree 2 situation, we'll end up with the root locus approaching zeros at infinity, okay, as k approaches infinity. And they will be along asymptotes at angles of pi on 2 and minus pi on 2. Okay, so eventually, as we increase k from a small value, k equal to 0, we start off with closed loop poles here and here, all right? And as we increase k, this one moves this way, this one moves this way. When they meet together, in order to continue satisfying the phase condition that defines the root locus plot, they split apart and one goes towards a 0 at infinity along this asymptote and the other one moves to a 0 at infinity along this asymptote. Okay, so you can see here that what's happening is that initially, as we increase k, all right, the system is, as a closed loop, is getting faster because this closed loop pole here is moving further away from the imaginary axis, and we know that as poles of transfer functions move further away from the imaginary axis, the transient parts of the step response decay faster. Okay, but beyond a certain point, we stop moving further away from the imaginary axis as we increase k, and all that happens is that the imaginary part of the pole becomes larger without the real part becoming more negative. Okay, so for values of k that put the closed loop poles here and here, they decay at the same rate as having a value of k that puts the poles here and here. All right. But the difference will be we will now get oscillations, and the frequency of the oscillation will be a function of the imaginary part. All right? So, you get benefit up to a certain point, and then you stop seeing the benefit as you continue to increase k. And that's happening because the constant gain controller is doing the same thing across all frequencies. And in this case here, you can see that increasing k, when we look at the Bode plots, is moving the crossover frequency to the right, Okay, and so you might associate that with faster response. It always gives you a smaller rise time in the response, all right? But if pushing the crossover frequency to the right like this results in a reduction of the phase margin, so the phase margin's huge when the crossover frequency is here and it's tiny here, right? You end up with a very poorly damped closed loop response, and that's consistent with having closed loop poles where the imaginary part is, larger or at least as significant as the real part, right? And so the issue here is that, sure, increasing the gain here is increasing the low frequency gain, which is required to get better steady state performance. It's pushing things to the right, which initially gives you faster response, right? Because over this range here, the phase margin's still good here, right? But you go too far, you end up with poor phase margin and very oscillatory response. Okay, so there's a limit to what you can achieve with proportional gain control. And really the problem is it's doing the same thing at all frequencies. All right? So pushing it up here to get better steady state performance, right? And initially faster performance ends up degrading your phase margin to the point where the response is not so great. Right? You can see the amount of time it takes to decay for the blue one is about the same as the green one. All right, so it's just going beyond the green one, it's just getting worse. All right, instead of better. Right, whereas going from the red to the green, at least it's getting faster. Okay. Sometimes, proportional gain can stabilise, right, but not always. So here's a situation where we start off with an open loop pole that is in the right half plane, so it's an unstable system, but a simple proportional gain controller will, for sufficiently large K, stabilise the system. It has to be sufficiently large so that the closed loop pole moves into the left half plane. So for very small gain, it's not going to stabilise, but for enough gain, it will stabilise. We've seen this sort of thing happening from the perspective of how the Nyquist plot can be made to encircle the critical point in an anti-clockwise direction as required for closed loop stability when you have one right half plane open loop pole with the gain expanding the Nyquist plot to create the encirclement needed. All right, but you can understand it from a really close plot. There are some plants that can't be stabilised by proportional gain control. Right, we've seen examples of that. So a double integrator, for example. All right, the root locus plot will look like this. It will just shoot up the imaginary axis. And of course, closed loop poles on the imaginary axis are not stable. All right, if you had a situation like a pendulum, but not like the one you're dealing with in the lab, and you had a right half plane pole that was further away from the imaginary axis than the left half plane one, then no matter how big the gain is, you would always end up with unstable closed loop. So there are situations where you need to use things that are more sophisticated than a constant gain controller. All right, because first and foremost, we need to make sure that we achieve closed loop stability. All right. Okay, you have to also be aware of increasing the gain at high frequencies where often the plant transfer function naturally has low gain. Physical systems often roll off at high frequency. Okay, they don't respond. When you start wheeling them too fast, they just don't move, right? So plant transfer functions often roll off. And if you're using high gain proportional control, all right, you can end up with the sensitivity function that tells you how sensitive the control signal, the output of the controller, is to the disturbances and the reference and noise and so forth, having high gain at high frequencies, okay, which can lead to actuator problems. So again, this is an issue associated with proportional gain control doing the same thing at all frequencies. All right, and so that motivates consideration of more sophisticated controller structures that can do different things at different frequencies. All right, and an example of that is a so-called phase lag compensator. So the structure of a phase lag compensator is as shown here. It has one pole, and 1, 0. They're both in the left half plane, right? So these coefficients tau and z and tau p are both positive numbers. So we've got a pole at s equals -1 on tau p and a 0 at s equals -1 on tau z. All right? And they're arranged in such a way that the pole at -1 on tau p is closer to the imaginary axis to the 0 at -1 on tau z. All right? So we haven't seen one of these before. We've seen one where these are swapped around, okay? But what this allows you to do is to increase the gain more. So this is showing what happens when k is equal to 1, right? So we've just normalised the low frequency gain to be 1 or 0 dB. But you can see what a compensator like this does is it increases, as we increase k, the gain at low frequency more than it does at high frequency. All right, so that's what you get by having the pole and the 0 in this order. Okay, so it's something that's often used to provide additional low frequency gain without significantly increasing the gain at high frequencies, which, as we saw in this situation, increasing the gain at high frequencies is what led to a reduction in the phase margin. All right, so in this situation we could have used a lag compensator to increase the gain here to get better steady state performance, perhaps for a ramp input, because for a step input we're already all good because there's an integrator at s equals 0, but we pay the price of reducing the phase margin because we're also pumping up the gain, which shifts the crossover frequency to the right. Okay, so a lag compensator won't necessarily do that. But there is a small price to pay, and the small price to pay is that you're always getting phase lag. That's why it's called a lag compensator, all right? And that's because, the phase due to the pole kicks down before the phase due to the 0, which kicks up, right? So, you're always adding negative phase to the loop. And adding negative phase to the loop is always going to degrade your phase margin, right? But if you put the crossover frequency well to the right of this point here, then you're only going to degrade it by a little bit relative to what it would be by just closing the loop around the plant transfer function with a constant gain. All right, so when using these sorts of compensators, you're usually using them just to fix stuff up at low frequency, and you make sure that the desired crossover frequency is well to the right of here. All right, so that the compensator is not making the situation any worse than the open loop situation from the perspective of phase margin. All right. A PI controller is just a special lag compensator with the pole at s equals 0. So what's happening is a PI controller just has the pole at the origin. All right, and often we put a pole at the origin in order to get 0 steady state error for step inputs, right? If there isn't already a pole at s equals 0 in the plant, or if we want 0 steady state error for plant input disturbances that are step-like. All right. So that's all a PI compensator is. It allows you to really pump up the gain, in fact make it infinite at 0 frequency. All right. And there's a 0 in there so that your controller, which if it were just an integrator, doesn't add phase at a crossover frequency, which you would probably try to make happen somewhere to the right of this, so that this compensator isn't making things any worse from a phase margin perspective than what would be achieved by just closing the loop around the plant transfer function. Okay. A lead compensator is something that we've seen before, and we've seen that it can improve the damping, right, of the closed loop response, and we've looked at that from the perspective of root locus plots, for example, and having a controller that has a 0 and a pole, and we've seen that can bring asymptotes, or at least the anchor point for asymptotes in the root locus plot, further to the left, right? How much by? Well, by that much divided by the relative degree. That's how much it'll move the anchor point into to the left, right? Which will, depending on how you set the gain, at least try to make the magnitude of the real part of the closed loop poles larger than the imaginary part. That's how you get better damping. All right? And you can see what it's doing because the phase, which is always positive for the zero, kicking in first, it's always adding positive phase to the open loop transfer function. Right? So you would use this sort of thing to improve things from the perspective of the phase margin at the desired crossover frequency, right? Because it's going to push you up from minus pi. Okay? So that's how these sorts of compensators are used, all right? And you can see that it's always going to sort of push the crossover frequency to the right a little bit, right? Because you usually line the crossover frequency up with this, where you're going to get the maximum phase, right? The phase comes back down again, right? Because the pole introduces negative phase. So this guy is giving you positive phase, at high frequencies it's giving you plus pi on 2, but this guy eventually kicks down, gives you minus pi on 2, so you've got pi on 2, minus pi on 2, it goes back to 0. All right? So you often use this by trying to choose the tau z and tau p, so choose the location of the pole and the 0, such that your desired crossover frequency lines up with the peak in the phase. But it's not it's not necessary to do that. Okay, you can place the crossover frequency here and still get the benefit of better phase margin when you put this in. Okay, but often we try to line it up with this. Okay, so it's something that's used to improve the phase margin at the desired crossover frequency. Right? Whereas the PI and the lag compensator are things that try to increase the gain at low frequency without interfering with what's happening at crossover. So this is about improving steady state performance, and this is about improving transient performance by improving the phase margin. Okay. A lead lag compensator and a PID compensator is just a special case. All right, is about putting a lag compensator and a lead compensator together. And the lag compensator is doing stuff at low frequencies, right? There's always a price to pay. It's always introducing phase lag, which is only ever going to make the phase margin worse. All right, and then there's the lead part of the compensator doing stuff at high frequency, giving you positive phase at higher frequencies, right? With a view to improving the phase margin, pushing you further away from minus pi radians. Okay, so a PID compensator is just a lead lag compensator with the poles at s equals 0 and minus infinity. Okay, so a PID compensator looks like which of course is not proper, right? So you can't really build one, okay? And so, the realisation of the PID compensator probably always really has another pole, right? With TP really, really, really small, right? So that 1 on TP is a large number, pushing that pole close to minus infinity. All right. So the point of combining two compensators is so you can do different things in different frequency regions, right? Use the lag part to increase the gain, right? These plots here are just showing what happens when the gain is 1, right? So of course, if I make the gain bigger than 1, it's just going to move all of this up without changing this. Okay. So the lag part can be used to increase the gain at low frequencies, the lead part to give you some phase, pushing you away from minus pi, assuming that you're going to put the crossover frequency somewhere around here. All right, so let's look at some examples now that I'm showing you just to give you a feeling for the sort of calculations you might do to choose these parameters. I certainly do not want you to think of this as a recipe for designing phase lag compensators, right? It's just to give you a feeling for the sorts of calculations you can do to pin down these parameters, right? So we've just seen roughly what these things can do, but it's rough. Now we want to, on the basis of some specifications, do some calculations that, determine values for these sorts of parameters. Okay, but don't think of it as a recipe. That would be a bad idea. All right. So, remember, this is what a phase lag compensator is doing, right? It's increasing the gain at low frequencies more than it does at high frequencies, but you pay a price. There's always phase lag. That's always going to push you closer to minus 180. It's never going to push you further away. Okay. So, a phase lag compensator might be the only thing you need if at the desired crossover frequency, the phase of the plant is already such that the phase margin is more than the specification. Okay? And accounting for the fact that a phase lag compensator will always have some phase lag. All right, but that phase lag will always be less than 0.1 radian if you choose the location of the zero such that it's a decade below the desired crossover frequency. All right, so when using a lag compensator, you want to make sure all of this stuff is going on well to the left of the desired crossover frequency. You're only using it to fix up stuff at low gain. You're not using it. It's only going to make things worse at crossover. So don't try to use it near crossover, right? And the way to ensure that you're not going to be, doing anything at the desired crossover frequency is to make sure that this zero, or 1 on tau z, which is the zero, is a number that's well to the left of the desired crossover frequency, so that the phase lag that this will be introducing is always less than 0.1. All right. So in a situation where you're trying to decide whether a phase lag compensator will be enough, perhaps to achieve your steady state performance objectives, if you check this, then there's a chance that that's all you'll have to do, just use a phase lag compensator. All right. So, this is a little example from the book by Chu and Zhao. So the plant looks like this. It has a pole at s equals 0. It has a pole at s equals minus 3, a pole at s equals minus 20, a 0 at minus 10. Okay, so there's already an integrator in our plant transfer function. Right, so our plant transfer function has this form. It's got an integrator and another transfer function. This transfer function is just all this stuff here. All right. If we were just to wrap a constant gain controller around this, we would get 0 steady state error for a step reference. All right. But we wouldn't get 0 steady state error for a ramp reference, right? If we go back to the analysis, well, I don't know, it's probably in another part of the notes. For a ramp reference, right, when you have an integrator in the plant, okay, you'll end up with a steady state error that's 1 on the constant gain controller, right, times this part of the plant evaluated at 0. Okay, so it's not going to be 0, all right, because that stuff there does not evaluate to 0, or it's not infinity, right, and k is a finite number. So this is just telling us, well, how much gain do we need at low frequency, right, in order to get a steady state error for a ramp reference of less than 0.05, right? So it gives you a lower bound on how much gain you need at low frequency. Right, the gain at low frequency of a lag compensator will just be k, right? Right, be the size of k. Here, it's normalised for k equals 1. If I make k bigger, this moves up. All right. So this is, as I've said, steady state stuff is all about what happens at 0 frequency. That's why I'm just focusing at 0 frequency. Right. At 0 frequency, this just looks like k. When I put S equals 0 in here, I'm just getting K. This looks like K at 0 frequency. That's why, we can just do all this analysis in terms of K. These parameters have no impact, right? So this is giving us a lower bound on K, right? Now let's suppose that, you're told that you don't want, for a step reference input, you don't want more than 20% overshoot, and you want a settling time that's less than 8 seconds, all right? Then, we can use these sorts of approximations, right, to translate that into a required phase margin and crossover frequency, right? So we want less than 20% overshoot. Overshoot's this curve here as a function of the damping ratio, right? That's telling us we want the damping to be, bigger than 0.45, all right? And a damping ratio bigger than 0.5 is the same as saying we want the phase margin to be more, on this part of the curve, more than 47 degrees, right? Or 47,980 times pi radians. Okay, so that's where, this stuff is coming from, all right? The settling time specification. So we know that the time constant of the closed loop is 1 on, based on, the approximation that says the complementary sensitivity function, is approximately canonical second order dynamics. The time constant is given by that. So 4 times the time constant will be roughly the settling time, and we want that to be less than 8. Okay? So that's equivalent to saying, well, we want the natural frequency of this, these dynamics to be greater than 0.5 on whatever we choose the damping to be, right? And we know that in order to meet the overshoot specification, we need the damping to be more than a certain amount. And then we can use the other curve that relates omega n and omega c to damping, right, to figure out a constraint on the crossover frequency, right? So it's just using this curve here. But, again, this is not a recipe. This is just giving you an example of the sort of things that you might do, right? It's not the only way to think about things. And it's certainly not a recipe. All right, so this is just about translating these time domain specifications into frequency domain specifications. And the thing to note is that we're just getting bounds here. We're not getting, one possibility. In order to meet this specification, we need the phase margin to be more than this, assuming that our, second order dominant dynamics approximation is valid, right? This is giving you a bound on the natural frequency, which gives you a bound on the crossover frequency. It's not just giving you one choice. There are many ways of satisfying these bounds, right? That's another reason you can't just treat this as a recipe. There's still choice here, all right? So let's just try choosing some numbers that satisfy these bounds, okay? This is telling us in order to get steady state error for a ramp reference of less than 0.5, we need K bigger than 15. Well, let's just take K to be 15. The smallest we can take it while meeting this specification, all right? And let's choose the crossover frequency to be 2, all right? So that this constraint will be satisfied with the damping set to be the smallest it can be while meeting this specification. So we're only just trying to meet our specifications, right? Of course you could make other choices which try to exceed the specifications that you're trying to meet. Okay, so don't be just looking for one number necessarily when doing design. There will always be choice, right? So, if we choose K to be this, and we choose omega C to be this, then we'll be consistent with our specifications, all right? We check the phase margin requirement, right, which is about making sure that if we're only using a lag compensator, which is not going to help us at crossover, that we're going to meet our phase margin specification, right, including some extra phase to account for the fact that our lag compensator is always going to give us phase lag, right? But if we make sure that the crossover frequency is well to the right of the location of the 0, then we're only going to get a little bit of phase lag. All right. So we've set this controller parameter. We've set this controller parameter to make sure the lag compensator doesn't interfere with the desired crossover frequency, or what's going to happen at the desired crossover frequency. We're going to rely on the phase of the open loop plant to satisfy our phase margin specification. We only have one parameter left, right? It's the location of the pole, right? And we now choose that parameter to make sure that at the crossover frequency, which we've set to 2, the magnitude of the open loop transfer function is equal to 1. Okay, so if you look at what the open loop transfer function is, what's it going to be in this case? Well, it's always this, right? Okay, and in our case, that's going to be K, right? Tau Z, J omega C plus 1, Tau P, J omega C plus 1, right? Times our plant transfer function. Okay. Now this guy here, on the basis of this setting, is just going to be approximately Tau Z on Tau P. All right? So so that's just the bit in the circle there. So making all of this equal to 1, right, when we take the magnitude of everything, is the same as saying, well, I want 1 on Tau P, so the 1 on Tau P, right, equal to 1 divided by Tau Z divided by K divided by the magnitude of G, right? So it's just about using all of these relationships to fix the parameters, right? We've got to make a choice eventually to end up with a controller that we can implement, right? You've got to fix those parameters to be able to implement the controller. All right. So you can see that we end up with a closed loop response shown in red for this controller than is better. In blue, that is better than the closed loop response that we would get by just choosing a proportional gain controller. All right, particularly from the perspective of the amount of overshoot that you get, right, without sacrificing much in terms of settling time. Okay. And the difference is about where the crossover frequency ends up being. With a constant gain controller, we've moved the crossover frequency much further to the right to a frequency where the phase of the open loop plant transfer function is too close to minus 180 degrees, right, which is giving us the bigger overshoot if we just use a proportional gain controller, right? Whereas putting the 0 of our lag compensator, further to the left relative to the desired crossover frequency, which is less than what you would get if you just used a proportional gain controller that satisfies the steady-state error specification, we end up with a crossover frequency where the phase of the open loop plant, which is sufficiently far away from minus 180 in order to meet the overshoot specification. All right? But, this wouldn't have worked out, for example, if we had chosen to have a crossover frequency that was 3 radians per second, right, which would still be consistent with all of these sorts of constraints that we've identified. Okay, and the reason is that the closed loop doesn't just have 2 poles, right, and we're making all of these assumptions here when translating time domain specifications into frequency domain specifications that relate to the closed loop behaviour being dominated by canonical second-order dynamics, right? But with this sort of controller structure, you're going to end up with 4 closed-loop poles, and so you may not end up with just 2 dominating, okay? So it's important when you follow a process like this to always go and check what your controller actually achieves, all right? Because, the translation here is based on an approximation, which may not hold. All right? And ultimately, these are the specifications that we want to satisfy. Okay, not these translated ones. These are the ones we need to check. All right? We get these from these on the basis of an approximation that may not hold. So you've got to be careful. That's why this can't be treated as a recipe. The point of showing you this is that you can use information, right, to choose the parameters of the compensator, K, tau Z, and tau P. Right? By just, checking steady state specifications, by, checking phase margin conditions, by checking the definition of crossover frequency. Definition of crossover frequency gave this equation here that allowed us to set one of the parameters once we'd chosen the other ones. Right? Just by the definition of crossover frequency. Crossover frequency is where the magnitude of the open loop transfer function is equal to 1, by definition. And we're using that to get an equation that gives us this parameter once we've chosen the other two. Right? That's what I'm trying to show you, right? Okay. So this is, just an integrator example. It's a lag. It's really, a PI controller really is a lag compensator, as we've already seen. All right. It gives you infinite gain at 0 frequency, right? Which might help you, meet a steady state error specification. Right? And in this case, it leads to exceeding a required specification, right? But you're never going to be able to use this thing to help you meet a phase margin specification, right? Unless you add another compensator. But you might be able to get away with not doing anything extra if your plant transfer function already has the right sort of phase to meet your phase margin specification at the desired crossover frequency. Right? When designing a PI compensator, you want to choose the location of the 0 such that this, right, and is well below the desired crossover frequency, which you would put over here so that you don't get the negative impact of there being some negative phase. All right? But again, you have to be careful. So we're following this procedure, but we end up with a very slow open loop transfer function 0, right? And, so you could end up with slow closed-loop dynamics, right? Because that's going to, one of the closed-loop poles, as we increase the gain, is going to pull you towards that open-loop 0. All right? So things don't always work out. And that's what's being shown here. All right? I'm not sure there's much point in rushing through a lead compensator example, so we'll leave that for next time. Sometimes if you don't, you go and do the check and you don't get what you want, like an example you saw, it's too slow, right? Yeah. Then you might try it after you can do it. Right, yeah. Right? But only after you see that you're not getting what you want when you just moving. Yeah. Okay. So it really depends on the situation. That's another reason they can't do this. Yeah. As soon as I'm showing these examples with particular transfer functions, if I change the plant transfer function and go through the same thing, I might get a different outcome. Yeah. Right? So it has to be done case by case, and all I'm trying to show you is the sort of calculations that you can do. Yeah. Right? Yeah. Just to give you a feeling for what those calculations look like, rather than saying this is the way you should always calculate it. Right? Yeah. Makes sense. Thanks. This is with a non-linear model for the pendulum or not? No, that's a linear model. That's a linear model. Why are you doing simulation with a linear model of the pendulum? What are you trying to do? What are you trying to do? The system identification part or the control part? The control part. Okay, so use the linear model then.